So we'll continue with whatever we left on the previous day. Okay. Hope this whiteboard is visible to you. One of you can confirm.
Yes,
Yes,
yes.
sir.
Yes, sir.
Okay. So we have seen, we have started with the isochoric process. And for this isochoric process, we saw what is the work done, what is the heat transfer, what is the change in internal energy, what is the change in enthalpy, and what is the change in entropy. Okay, we have seen all these things. Okay, and apart from that, we have also seen how to draw the PV diagram for all the five processes. Okay, so we will continue on this. Now we will talk about the isobaric process where pressure is equal to constant. So now we will talk about isobaric process. And you know, for the work done, we have seen it is P times V2 minus V1. We have already seen the proof of this when we discussed work transfer. Okay. And then when you talk about internal energy, the general equation for internal energy in the last class we saw it is mcv into T2 minus T1. Okay, if you want me to recall it again, we said the definition of um, CV is partial U, partial T at constant V. Okay, and so we said because it is dependent on this internal energy is a function of temperature only, and so you can write this as du by dt also, and so you can write du as cv times dt. Okay, this is specific internal energy and this is specific heat, everything in small. So when you integrate it on both sides, you will get delta u, small u, cv times delta t, which is T2 minus T1. And if you want to convert it into internal energy, specific internal energy to internal energy, you multiply with mass on both sides. And so you get mcv times T2 minus T1. So the change in internal energy will, the general equation will be mcv times T2 minus T1. Similarly, in the last class, we also saw delta H is mcp times T2 minus T1. Okay, so just like we started cv equal to partial u partial t, you can also start cp, sorry, cp is equal to cp is equal to uh, partial h partial t at constant p. You can start with this. Okay, and you can follow the same steps and you will get delta H is mcp times T2 minus T1. So that will be the case here also. So this will be mcp times T2 minus T1, and you will find for Q the heat transfer into for a pressure equal to constant. This is a constant pressure process. So you can write this as mcp times T2 minus T1. If you look at volume equal to constant for the isochoric process, your heat transfer was mcv times T2 minus T1 because volume is held constant and so you have Cv. Your pressure is held constant, so you have Cp. If you have doubts, as I already told you, you can apply the first law of thermodynamics, which is delta U plus W. Okay, so delta U here is mcv times T2 minus T1, and here W you have V times V2 minus V1. Okay, and we know ideal gas equation of state where PV is equal to MRT. Okay, so for PV I can replace with MRT. Pressure is held constant, so uh, you can write this in two steps. No change in MCV into T2 minus T1. here you can say this can be written as P2V2 minus P1V1. There is no harm in writing like this because pressure is held constant. So because it is a constant pressure process for a constant pressure process, P equal to P2 equal to P1. So I can write PV2 minus PV1 as P2V2 minus P1V1 for my convenience. And I can apply the ideal gas equation of state where I can replace P2V2 with MRT2 and P1V1 with MRT1. Okay. And so now what I have is into MCV into T2 minus T1, and this MR can be taken as common, and you will have MR times T2 minus T1. And now if you look at both these equations, M and T2 minus T1 are common, so you can take M into T2 minus T1 as common on the outside, and in the inside you will have CV minus R. And we know definition of R is Cp minus Cv. So Cv minus R is going to be Cp. Okay, is that correct? Have you made some mistake somewhere here? So Cp, this should be R plus Cv, right?
Yes, sir.
Okay, so we have to go to the process once again. In a normal sense, W is P times V2 minus V1. And this guy, you can see that this is V2 and this is V1 if you extend it to the x-axis. Okay, and we call this as P times V2 minus V1. And you can see that this guy is isobaric compression. So isobaric compression is work input. So to compress something, you are supposed to give work in the form of input to the cylinder piston arrangement. You should push the piston to compress it. And once the combustion process takes place, the gas will push the piston downwards. So that is work done by the gas. Now this is work done on the gas by the piston. So this guy is supposed to be negative. Okay. So when you take work input, are you able to understand this point? So this guy is supposed to be work input. So if it is work input, then this guy should be minus. This guy should be minus over here. So if it is minus, then what you will have is CV plus R, and that would be CP. So don't think that I'm taking this to my convenience. Uh, so whenever they write this first law we write it as Q is equal to delta U plus W, right? So people, they write this as Q in is equal to delta U plus, or the other way around, delta U is equal to Q in minus W on. Okay, so this is how people usually write this. Delta U is Qn minus W1, which means heat addition minus work done on the system. Work done on the system is the work input. So it is usually Qn and W on. So that is why you will get MCP into T2 minus T1. Okay, so you will get Q equal to MCP T2 minus T1 if you apply the first law of thermodynamics also. Okay, and one more guy which is left out is delta S. So we have seen W, we have seen already Q, delta U, delta H. The next guy is delta S. I'll go to the next page and then I'll come back so that if you need time to copy, you can copy. So delta S, I have told you the definition of it. That is integral of dq by t. So just now we saw Q is mCp times T2 minus T1. This T2 minus T1 is nothing but dt. So I can write this. So if I write this as dt, or let me write it in two steps so that we can avoid confusion. So Q, we write this as mCp dt T2 minus T1. And if I write this as dt, then the left hand side can also be written as dq. Okay, and so dq is mCp times dt, and which can be substituted over here. Now we are doing for the isobaric process. Okay, and so this m is constant for a closed system. Cp is also a constant. So mCp can be taken outside the integral limits. So you get dt by t. The limit is usually between state point 1 and state point 2. So what you have is mCp times ln of T. The temperature at state point 1 is T1. The temperature at state point 2 is T2. So mCp times ln T2 minus ln T1 within the brackets. And applying the logarithmic rule, we can write this as mCp times ln of T2 by T1. So let's proceed to the next process, which is isothermal process. And listen very carefully, all of you, listen very carefully. This is where students make a lot of mistakes over here. Isothermal process, temperature equal to constant. You can also write this as PV equal to constant. How PV equal to constant? We have done so many times, so I'm not going to do it again. So temperature equal to constant. Work done, you know, it is P1 V1 times ln of T2 by T1. Karthik, you are going to tell me what is the value of heat transfer for an isothermal process. For an isothermal process, temperature is constant. What is the heat transfer for an isothermal process? Karthik sir,
Sir, yes, sir.
what is heat transfer for an isothermal process? What value will you have?
Sir, T is 0 and del T is 0, sir.
So
Sir, you're asking about T only, no, sir.
what is the value of Q? What is heat transfer for an isothermal process?
Sir, 0, sir.
So Q is equal to 0. Is there anyone in the class who says it is not 0? There are 50 students in the class. So is there anyone who says it is non-zero? So everyone agrees that it is 0, but unfortunately, this
So
is
it's
wrong.
constant, sir.
Your Q is not equal to 0. We said it is only temperature equal to constant. I never said it is an adiabatic process. In an adiabatic process, there is no heat transfer. So for an adiabatic process, Q is equal to 0. That is known. but this is only temperature is equal to constant. Okay, so now if you look at delta U, your delta U is mCv times T2 minus T1. This is a general equation. So your delta U is going to be equal to 0 because this T2 minus T1 is equal to 0. Okay. So now if you apply the first law of thermodynamics, Q is equal to delta U plus W. So delta U is already 0 and W is not equal to 0, which means your Q should be equal to W. You get it? So when you say Q is equal to 0, then that violates the first law of thermodynamics. So your Q is also equal to P1 V1 times ln of T2 by T1. Do you understand this? Okay. So when you say Q is equal to 0, you mean this delta U. Only delta U is mCv times T2 minus T1. And what about delta H? Delta H is mCp times T2 minus T1. And this guy is also 0. So the change in internal energy, the change in enthalpy, they are 0. But your work transfer is equal to heat transfer. So your heat transfer will be P1 V1 times ln of P2 by T1 because you have to consider the energy balance. Okay, is that clear? So this is somewhere you have to be very careful. Sometimes people ask this even in competitive exams like GATE. So for GATE also such kind of questions have turned out. Okay, so you have to be very clear here. So your heat transfer is equal to P1 V1 times ln of T2 by T1. But delta U and delta H, they are 0 because T2 minus T1 is 0. What about delta S? Delta S, this is going to be integral of dq by t. Okay. And here, this is going to be slightly different because I can't have dq from this equation. So instead, what we will do is we will use q by t. I have told you ds is dq by t. So when I integrate it on both sides, I get delta S is equal to Q by T. In the previous cases, we cannot use this form Q by T, and so we took integral of dq by T. In this case, we can't use integral of dq by T, so we use the form Q by T. So to avoid confusion, let me remove this equal to, and so I can write this as delta S is equal to Q by T. Q here is V1 V1 times ln of V2 by V1 whole divided by T. And we have seen, well, while we derived this W equal to P1 V1 times ln of P2 by P1, this P1 V1 is constant, which can also be written as Pv times ln of V2 by V1 whole divided by T. And this Pv guy is nothing but MRP ln of V2 by V1 whole divided by T. So I can cancel out this T and this T over here. And this is simply Mr times ln of V2 by V1. Or if you want, we have already seen this V2 by V1 can be replaced by V1 by V2 also. Okay, so this is how you get the value for the change in entropy. So delta S is Mr times ln of V1 by V2. Is that clear? So how we get Q is equal to W? Okay, so the next time, none of you should make this mistake. So this is a common mistake everyone tends to make. They say Q equal to 0, but Q is not equal to 0. Q is equal to W, whereas delta U and delta H are 0. Is that clear? Okay. And then what we have is isentropic process. So what is this isentropic process? We said this isentropic process is entropy equal to constant. So when I say entropy, then it should be capital S. Okay. And we define this isentropic process as reversible adiabatic process. So this is a reversible adiabatic process. Okay, so when I say adiabatic, then there is no heat transfer. So Q is equal to 0. And we know work done is P2V2 minus P1V1 by 1 minus gamma. Okay, and delta U is going to be the same, which is mCV times T2 minus T1, and delta H is going to be mCP times T2 minus T1. What about entropy delta S? So this is entropy equal to constant, so change in entropy is going to be equal to 0. Okay, and we know that the equation for this is PV power gamma equal to constant. Is that clear? So Q is 0, delta S is 0, W we have already derived, delta U and delta H, they have the same general equation mCV times T2 minus T1 and mCP times T2 minus T1 respectively. Okay, very simple. But before moving on to the next process, sometimes people ask us to prove for an adiabatic process PV power gamma equal to constant. Sometimes they ask this in a 6 mark question, 6 marks or 7 marks, sometimes 10 marks also. So how do you say that for an adiabatic process PV power gamma equal to constant? So sometimes this question has turned out in the question paper as well. So we will see how to prove this. Okay. So we will start with the first law of thermodynamics. We will say delta Q is du plus delta W. You know what this means? This is an inexact differential, this is an inexact differential, and this is an exact differential. These two are path functions, and this is a point function. Okay. And what do we know so far? An adiabatic process, sorry, here the question should be isentropic. So for an isentropic process, prove PV power gamma equal to constant. We know that isentropic is a reversible adiabatic. So for an adiabatic process, we know delta Q is supposed to be equal to 0. So if you apply that in the above equation, this turns out to be du plus delta W equal to 0. And for this du, from the definition of CV, I can write this as CV times dt. If you remember, CV was defined as partial u, partial t at constant v, and I said we can write this as du by dt as well. So du becomes, sorry, not partial, this guy is supposed to be d, du by dt. So du is cv times dt. So I replace this with cv times dt. Okay. And we know that this delta W for a closed system, we can take that as PdV. If it is dW, we can write this as PdV. So we have written this as PdV equal to 0. Okay. So this becomes the base equation. Let's take this as equation number 1. Okay. And let me consider the ideal gas equation of state. So what is ideal gas equation of state? P small v is equal to RT. Okay, so that is my second base equation. Okay, and if I differentiate this second equation, differentiating on both sides, you have to follow me and you have to keep writing along with me. Differentiating on both sides, which means d of PV equal to d of RT. And we have already seen the mathematical equation for d of xy. D of xy is x dy plus y dx. So here you can write this as PdV plus VdP, and this R dt plus ddr, R is a constant, so dr will be 0, so you won't have the second term. You will simply have R times dt. Okay, and now I can write dt is PdV plus VdP divided by R. Okay, and let me call this as equation number 3. Okay, I hope things are clear up to this. This is just for your note. Okay, now what I'm going to do is, let me substitute for dt, which is equation 3, in equation 1. So dt, I'm going to substitute it over here. So Cv times Vdv plus Vdp divided by R plus Vdv, this is equal to 0. And if you open the brackets, you will find Cv by R times Vdv plus Cv by R times Vdp plus Vdv equal to 0. Okay, and here you can see there is one PdV over here and there is another PdV over here. You can couple these two terms. So you will have PdV times Cv by R plus 1 plus Cv by R times Vdp equal to 0. And if you take this 1 plus Cv by R, or uh, we, we, we will skip this because this is not going to fetch us any result. Instead, what we will do is, we will say you have R here in the denominator. Here there is no denominator, so you can multiply this with R over here and take this to the right hand side so that this R gets eliminated in the denominator. So this is Cv times Vdv plus Cv times Vdp plus R times Vdv equal to 0. Okay. And now what I can do is, I can replace this R with Cp minus Cv. We know that R is Cp minus Cv. So let me introduce or substitute that Cp minus Cv over here. So let me see what I get. So Cv times Pdv plus Cv times Vdp plus Cp minus Cv times Pdv, and that is equal to 0. And let us expand that and see what we get. Cv times Pdv plus Cv times Vdp plus Cp times Pdv minus Cv times Pdv and equate it to 0. This guy is Cv. This guy is Cv. Okay, and you can see that I have a Cv times Pdv over here. This is a positive entity and this is a negative entity, so I can cancel out these two guys. Okay, and what is remaining is Cv times Vdp plus Cp times Pdv, and this is equated to 0. Okay, And now what I'm going to do is mathematically, so let me say, let me call this as equation number 4. So now what I'm going to do is, so this is for your note. So dividing equation number 4 with PV times CV. I'm going to divide it everywhere equally so that it doesn't violate any mathematical principle. So I'm going to divide CV times VDP by PV times CV plus CP times VDV with PV times CV, and this is equated to 0. And now let's see what happens. And I will be able to cancel out this V and this V. I will be able to cancel out this CV and CV. And here I'm able to cancel out this P and P. Okay. And so what I have got is dP by P. And here what I have is Cp by Cv times dV by V. And what is this Cp by Cv? So we have seen Cp by Cv is the specific heat ratio, which is gamma. So what you have here is dP by P plus gamma times dV by V, which is equal to 0. Okay. And if I integrate it on both sides, integrating the, or let's call this as, let's call this as equation number 5, integrating equation 5 on both sides, you will get dP by P is ln P, and gamma is a guy which is held constant, so this is gamma ln V, and integrating 0 will give you some constant which we can call as ln C. Okay, and applying the logarithmic rule, this gamma times ln V, that can be written as ln of V power gamma. Gamma times ln V can be written as ln of V power gamma. Applying the logarithmic rule, you can check this logarithmic rule. If you want me to write this, a ln V is nothing but ln of V to the power a. So that is the rule. That is the logarithmic rule. So we are applying that rule. So gamma times ln V is going to be ln times V power gamma. And here you have ln C. The next logarithmic rule is ln P plus ln V power gamma. So this can be written as ln of PV power gamma equal to ln C. And if you take anti-logarithm, or if you cancel out the logarithmic terms on both sides, you will have PV power gamma equal to constant. So this is how we say for a reversible adiabatic process, PV power gamma is equal to constant. Okay, a systematic derivation, a simple derivation. So we have seen till isentropic process. The only process that is left out is the polytropic process. So for the polytropic process, PV power n is equal to constant. Okay, and even in the previous cases, I haven't uh, stressed on this, but that is very simple. So here you can write, so just like I told you, the small v can be converted to capital V and capital V can be converted to small v, provided the units match. Okay, you can write it like this because PV power n is equal to constant. And sometimes in the question paper, they ask you to find Not necessarily the semester exam, maybe in competitive exams also. Sometimes they ask you to find the value of this index. Okay, so how do you find the value of the index? So you can write this as P2 by P1 equal to V1 by V2 whole to the power n. We will come to finding that index also. Okay, so P2 by P1 is V1 by V2 whole to the power n. So you can use that as one relationship. The other relationship is between pressure and temperature also, or temperature and volume also. If you want, you can write it. So in the previous class, I told you this PV by T equal to constant, which is the ideal gas equation of state. So you can write this as P1 V1 by T1 equal to P2 V2 by T2. And here, if I want to find P2 by T1, okay, and then what we have here on the right hand side is P2 V2 minus by P1 V1, and I already have a P2 by P1 times V2 by V1. And now you can substitute for this P2 by P1 over here. And that guy is V1 by V2 whole to the power n, which is multiplied by V2 by V1. And so you will have V1, and see this in the numerator you have to the power 1. And if this V1 is brought back to the numerator, it will be V1 to the power minus 1. So you have V1 to the power n minus 1. Similarly, V2 in the denominator, you have power n, and if this V2 is brought down to the denominator, and this guy will also be V2 to the power n minus 1. So it is V1 by V2 whole to the power n minus 1. Or you can write V1 by V2 is T2 by T1 whole to the power 1 by n minus 1. This is also possible. And this guy can be written as V1 by V2 is equal to P2 by P1 whole to the power 1 by n. This is also possible. And here I have a relationship between volume and pressure. Here I have a relationship between volume and temperature. If you want the relationship between temperature and pressure, instead of substituting for P2 by P1, you can substitute for V2 by V1 over here. And here you have V1 by V2. And so you can write this as P1 by P2 whole to the power n. Okay. So here you have V1 by V2. And this guy, if I write this as V2 by V1, if I interchange, you will have P2 by P1 whole to the power 1 by n. And if I want to find T2 by T1, so I retain P2 by P1 and I replace P2 by P1 with P1 by P2 whole to the power 1 by n. So what you have is P2 by P1 whole to the power 1 by n minus 1, which is P2 by P1 whole to the power 1 minus n by n. Uh, so when I interchange V2 by V1, P1 goes to the numerator, which means this guy is supposed to be n. Am I right? Am I right in writing this as P1 by P2 to the power n? Or let us do the other way around. What we require is V2 by V1. So V2 power n by V1 power n is P1 by P2. So it is P1 by P2 to the power 1 by n. So that is the previous one is correct. So this guy is supposed to be 1 by n. So whenever you have confusion, you can just check that. So V2 by V1 is P1 by P2 whole to the power 1 by n. Okay, so you can have all these relationships t2 by t1. So if this is going to be t1 by t2, you will have p1 by p2 whole to the power 1 minus n by n. Okay, so all these relationships you can have, so you need not memorize them. Just like I derive, you can derive this when it is being asked. Okay, the next one is finding the index. Finding the index, which is n. You have PV power n equal to constant, right? This n is what is called as the index. So how do I get that? So you can take P1 V1 power n equal to P2 V2 power n. And if you take ln on both sides, ln P1 V1 power n equal to ln P2 V2 power n. Now just we have to go the reverse order. So I can write this as ln P1 plus ln V1 power n, which is equal to ln P2 plus ln V2 power n. And I can once again write this as ln P1 plus n ln V1 equal to ln P2 plus n ln, we are using capital everywhere, so let this guy also be capital. Erase this. N ln V2, and so what you'll have is ln P1 minus, uh, we will do the other way around, n ln V1 minus n ln V2. Sorry guys, everywhere it is capital, so we will write this as capital. This is equal to ln P2 minus ln P1. Once again, applying the logarithmic rule, ln V, it automatically comes to me like that one, ln V2. Sorry about that. And this is equal to ln P2 minus ln P1. And according to the logarithmic rule, we can write this as n of ln V1 by V2, which is equal to ln P2 by P1. And so if I want to find the value of n, it is ln of P2 by P1 divided by ln of V1 by P2. Is that clear? So sometimes in the problem, they give you the values of the state points, and sometimes they ask you to find out the value of this n also. So they ask you to find the value of the index of compression or expansion. Sometimes that also happens. Okay. Is that clear?
Yes, sir.
So just like we did for the previous case, here W is P2 V2 minus P1 V1 by n minus n delta U. What about delta U? That guy is MCV times T2 minus T1, and delta H is MCP times T2 minus T1. Okay, so that is a general expression. So this guy is MCV times T2 minus T1, and delta H is MCP times T2 minus T1. And now for heat transfer, if you take, you have to apply the first law of thermodynamics. There is no other go. So delta U is mCV times T2 minus T1, and this guy is P2 V2 minus P1 V1 by 1 minus N. Okay, and so what you will be getting is, for the time being, We will stop it here as MCN into T2 minus T1. There is one another derivation over here, but I don't want to do it in today's class because just now we have seen PV power gamma equal to constant. So I want you to practice that first, and then we will come back to a specific equation which we can get for the heat transfer. Okay, so here for a polytropic process, so this we are doing for PV power n equal to constant. Okay, so this is what we have, and delta S, because you have MCN, so that would be taken as MCN BP. So you will have MCN times ln of T2 by T1. Okay, so that is what you will have for the polytropic process. So I'll stop here with the derivation part. So here for the various processes, how, what is the work done? So you can see the work done for an isobaric process, it's 0, and we have derived all this. And I have skipped PV power gamma equal to constant because wherever you have got n, you have to simply replace it by gamma. Wherever you have n, you have to replace it by gamma. Okay, so that is why I haven't included that. And so for the isentropic process, you will have the change in entropy as 0. You will have the same MCP times T2 minus T1. And for an isentropic process, your heat transfer will also be equal to 0 because it is a reversible adiabatic process. This guy will be MCV times T2 minus T1, and this guy will be P2V2 minus T1V1 by 1 minus gamma. Okay, and so this table you can remember, but I won't encourage you to memorize this. Memorizing won't help you in the longer run. You see, while I am deriving it, I am not recalling it from my memory. All that I remember is the base equation. The base equation is PV power gamma equal to constant. That is what you have to remember. The other base equation is W equal to integral PdV. Then you integrate it. Okay, so that is how you have to remember the formula. Okay, P2 V2 minus P1 V1 by 1 minus gamma. I don't remember it all the time. Many times in my memory, I wonder whether it is 1 minus gamma or gamma minus 1. I don't memorize it. I just derive it and see whether it is 1 minus gamma or gamma minus 1. Okay, so that is how you guys, I encourage you guys also to derive them and not memorize them. The base equations are what, that is what is supposed to be there in your memory, not the entire table. But if someone prefers someone prefers whose memory is very strong, you can go for it, but I don't encourage that because that is not the way by which you are going to study thermodynamics. Okay? And now let's use this and solve a couple of problems here. Okay, so let's take this example. Those who those who are not listening carefully so far, please at least start listening now. Okay, now we are into problem solving, not into the derivational part, where some people feel bored when I start taking the derivations. And that's why I stopped with one more derivation is there, and which we will do it in the next class. Okay, so now let's look at this example. A certain gas occupies a volume of 0.3 meter cube at a pressure of 2 bar. The moment you start reading, you can write down the given equations. So here I can see that volume is 0.3 meter cube. It's the initial state and the initial pressure is 2 bar. The temperature of gas at the state is 350 by 350 Kelvin. So T1 is 350 Kelvin. The gas undergoes a thermodynamic constant volume process. Okay, so here they have very clearly mentioned that it is a constant volume process, which means V1 is equal to V2. So there is no change in volume. The pressure rises to 7 bar, so P2 is 7 bar. Determine the temperature at the end of the process. So they want you to find what is the temperature at state point 2. what is the change in the internal energy, and what is the change in enthalpy, and what is the change in the entropy during the process. Take CV, they have given the value of CV and they have given the value of R, and they have said it is in kilojoule per kilogram Kelvin. Okay. And when we substituted a joule, so you have to multiply it by 10 to the power 3. So these are all the given details. Now let's go step by step. The first question is they want us to find the value of this temperature. Okay. So it is, so let's say solution, it is a constant volume process. So an ideal gas equation of state, we say PdT is equal to constant, which means I can write P1 V1 by T1 is equal to P2 V2 by T2. In this case, V1 and V2 are the same, they are constant, so I can cancel out V1 and V2, which gives me T2 by T1 is P2 by P1, and they want me to find the value of the temperature T2. So T2 is T1 times P2 by P1. I hope you are all listening. See, unless you listen and follow, it will be difficult. If you are listening and following, it will be very simple. But if you are not listening, then it will be very difficult for you. So T1, it is 350. P2 is 7 divided by 1. And both cases it is bar, but for avoiding any confusion, you can write 10 to the power 5 in both the cases. So 7 into 350, so that would be your final temperature T2. So let's see, or let's
Sir,
calculate.
P1 2 bar.
Sorry, please come
Sir,
again.
P1 2 bar.
P P1, sir. No.
So T2 is, have I written something wrongly? I don't get what
Sir,
you are saying.
P1 is 2 bar, sir.
Oh, P1 is 2 bar. Okay, okay. So instead of 1, I should have written. Okay, good. So, so it is 350 into 7 divided by 2. That gives you 1225 Kelvin, right? So I have answered the first question, which is the temperature at the end of the process. So we have answered one question. What is the second question? The change in internal energy. So change in internal energy is mCV times T2 minus T1. Okay. I know the value of CV, I know the value of T2, I know the value of T1, but I don't know the value of M. But I can get it using the ideal gas equation of state. P1 V1 equal to MR P1 and M is equal to P1 V1 by R T1. P1 is 2 bar, volume V1 is zero point 0.3, R is given as 0.287 into, this is kilojoules, so I'll write this as 287, 0.287 into 10 to the power 3. T1 is 350 Kelvin. And so now if you substitute this in the calculator, 2 into 10 to the power 5 multiplied by zero point 0.3 divided by 287 and divided by 350 Kelvin, you get 0.597, and I can take this as zero point 0.6 kilogram. 0.6 kilogram is the mass. And so if I substitute it over here, this is 0.6 multiplied by CV is 712. T2 is 1225 minus 350. So this guy will give you the change in internal energy, and if you want, you can write it in kilojoules. So 0.6, CV is 712, 1225 minus, so that is 373.8 kilojoules. Okay, so that is your delta U. Similarly, you can calculate delta H. which is mCp into T2 minus T1. Can anyone help me to get the value of Cp? How will you get the value of Cp?
R equal to C.
R is equal to CP minus CV.
Very good.
Cp
So
value.
R is equal to Cp minus Cv. So Cp is going to be R plus Cp. So 287 plus 712. So how much do we get? So 2 plus 7 is 9. 8 plus 1 is 9. 999 kilojoule per kilogram Kelvin. Okay. So mass is 0.6 multiplied by 999. Is my addition correct? If it is wrong, you can let me know. If it is correct, it is okay.
Sorry, into 10 to the power 3.
No. 280, 0.287, 0.287 plus 0.712. So that would be 0.999. Oh, okay. 0.999 kilojoule per kilogram Kelvin. Okay. And in this case, it is just joule per kilogram Kelvin. Is that clear now? If you are doing it in point, then that is kilojoule. If you are already converted to joule, then it is simply joule per kilogram Kelvin. Is it okay?
Okay, sir.
So 0.6 into 999 into 1225 minus 3. So that guy is 524.475 kilojoule, or you can simply write 524.5 kilojoules. And the last part is delta S. So this is the constant volume process. So if you have forgotten, I'll just erase this part so that we can use this space to derive this. So delta S, this is going to be integral of dq by t, and remember dq is mcv dt. So integral of mcv dt by t. So mcv can be taken outside the brackets, and that is ln t between the limits t1 and t2. So that is mcv times ln of t2 by t1. So you can just derive it. You need not memorize this. So mcv times ln of t2 by t1. So 0.6 into 712 into ln of 1225 by 350, and this will give you the answer. So 1225 by 350, take ln multiplied by 712 into 0.6. So this guy is 535.18, but the answer is in joule per Kelvin 1.